Alright friends, welcome back. This is going to be part 2 of your section 4.1 videos, and in this video specifically we're going to be talking about rational functions. So let's get started with that, right? So a rational function, remember, we took a look at rational expressions a chapter or two ago. Basically that's just an algebraic expression that looks like a polynomial over a polynomial. So it's a ratio of polynomials. And so if you take a look at your most basic type of rational function, we would just basically take a look at one of the most basic types of a polynomial over a polynomial. And that is to say a linear over a linear, something that might look like mx plus b, okay? I want to do the same thing as in this video that we did in the previous video talking about reciprocal functions, where we're just taking a look at basic different characteristics of the graph and then using those to find different various things that they might be asking us for. And so you'll notice that I've got a lot of the examples in this video already done out, so we just kind of talk about them, okay? So the shape of the graph of a basic rational function is going to be a hyperbola, just like it was for the reciprocal functions, and we could basically just go through and find their asymptotes and the domain and range in the exact same way. So if you're looking at an example like part A here, it looks like I can have a vertical asymptote at x is equal to -4, a horizontal asymptote at y is equal to 2. Again, for more background on how to figure those asymptotes out by looking at the graph, make sure to watch the previous video, part 1. And then from those asymptotes, we get the domain and range, so that's pretty simple. In the next example here, same thing, right? So we can go ahead and go through and find the vertical and horizontal asymptotes and then use that information to figure out the domain and the range, okay? Now, again, you do enough of these examples and you start to notice patterns, and those patterns lead to rules, and then you prove that those rules are always true and that they always work, and then you can use them as tools to solve problems. And so while we're not going to do that here in this video, what I do want to do is go ahead and just kind of introduce some of those rules to you so that we can use them as shortcuts to get various different characteristics of our graphs so we can make nice pictures, okay? Here in example 4, we're just doing more of the same. We have a nice function over here. This is something that I taught you guys how to do in the previous video talking about reciprocal functions, so I'm not going to dive too deep into it here, but basically we would just want to use the TI-84 to get some nice table of values. Make sure to draw in your vertical and horizontal asymptotes, and then draw a nice sketch of the rest of the graph of your rational function, okay? Now those are basic types, a linear over a linear. What we're going to be seeing here in class is a bunch of different examples where we might have a quadratic over a linear, so a degree 2 over a degree 1, or maybe a degree 1 over a degree 2, or maybe even throw in some cubics, degree 3s in there. I don't think we're going to be getting too much involved into higher degrees than these. And so I basically just for the rest of the video want to go ahead and show you some shortcuts that you can use for being able to do that, okay? What we need to be familiar with, though, are all the different characteristics of these types of functions that could come up. So when you start kicking the degree higher and higher and taking a look at polynomials that are maybe quadratics or cubics or something like that, you're going to introduce this concept of there maybe being a hole in the graph. And so what that is basically if you take a look at a graph and the curve is as such, this is kind of a weird concept, but the idea is that there is an input that is unfortunately not going to have an output. So literally on the path of the graph, we would have a little bit of an open circle there. If you have ever walked down the sidewalk and there is a manhole for a sewer on the sidewalk, right? And if that manhole did not have a cover, then that would just be a big hole in the ground that you would have to make sure that you step over. That's literally the exact same idea here. We get the entire rest of the path of the graph, but then we would have to step over that hole and then continue walking along our sidewalk here, okay? So holes are going to come up when we start taking a look at rational functions with higher degrees, and so to find them algebraically, I've given you a nice step-by-step process here for being able to do that. And instead of strictly reading through them just by themselves, I just want to take you through an example where we're finding some holes of a rational function, okay? So here's part A, f of x is equal to x squared minus 4 all over x squared minus x minus 6. So this is a degree 2 over a degree 2. And if you read the guidelines from up above, the first step in order to find your holes in this graph is step 1, it's going to say to factor the numerator and denominator. So we are going to need to remember how to factor polynomials. That's something that we've talked about in previous videos, and so if you want to go back and reference that, that would be your section P.4 videos. We are going to have to factor the numerator, which is the top, and the denominator, which is the bottom. And so let's just do that really quickly. It looks like the top is the difference of two squares. That would factor into x plus 2, x minus 2, and then the denominator, that's just a trinomial, so we could factor that into two sets of parentheses, x and x, and then some combination of 2 and 3 I think would work out nicely. How about a positive 2 and a negative 3? I think that would work out perfectly, okay? And so we have factored the numerator and the denominator, and so that's step 1. If we come back up here to step 2, it says if there is the same factor in the numerator and denominator, then there is a whole, okay? And so if they do have the same factor in the numerator and denominator, that would be something that could cancel out for us, and then we could continue. And so if we look at our example down here, we definitely see that, right? We have x plus 2 over x plus 2. All right, and so what that means is that those factors would simply cancel for us, and we can go ahead and write a more simple version of the function here, and that would be x minus 2 over x minus 3. All right. Now, how do we get the whole? Well, if you go ahead and continue reading the steps from up above, it'll say in step 3 that what we want to do is we want to take that factor that we noticed was the same in the top and the bottom, so the same one that we talked about in step 2, and we basically just want to go ahead and set it equal to 0 and solve, okay? And it says here in step 4, the solution is the x value of the whole. All right, and so if we come down here, the factor that we noticed was the same in the numerator and denominator, of course, was x plus 2. We want to set that equal to 0 and then solve this little equation. That's just a simple one-stepper. So that's going to be x is equal to negative 2. And according to the steps from up above, that is going to be the x-coordinate for our whole. So over here, I'll go ahead and start to write our answer. We'll say that there's going to be a whole at a point with these coordinates. We just figured out the x-coordinate. That's going to be negative 2. Okay? Now, continuing with the steps up here, number 5, it says now simplify the rational function, which means, of course, cancel the common factors in the top and bottom. We already went ahead and did that. And then it says in step 6 to plug the x value of the whole into the simplified rational function. Okay, so the simplified one, that is the one that we got after canceling those terms out. And so for our purposes, that's going to be this right here. All right, the reason that we don't want to plug in your negative 2 into the original is because the original still had this factor before canceling. And if you plug negative 2 in there, it's going to result in 0, which is going to make the whole denominator equal to 0. And that's not something that we can have. So that's why we're going to take our x value and plug it into our simplified version where we're not going to be having any issues with 0 in the denominator here. And so if I plug in negative 2, then that's going to be something I plug into the top and into the bottom. All right, and then I can go ahead and continue here by figuring that out, right? So in the top, I'm going to get negative 4. In the bottom, I'm going to get negative 5. And that's a negative divided by a negative, and that's going to result in a positive fraction, which is 4/5, and that is going to be the y-coordinate for the whole, okay? And so it looks like we ended up with a fraction y-coordinate there, which is fine. But that tells us how we can go through and find the whole of a rational function, okay? So we just want to follow the steps from up above. We just want to factor the numerator and denominator and then go through and cancel out any common factors. I don't know why, but OneNote just took me to the very end of my notes here, so I'm going to have to scroll back up. Here we go. And then continue in that way, okay? Part B I've already done just for the sake of speed here in the video. If you factor the numerator, which is a quadratic, it looks like that's going to have a common factor with the bottom, and because we can cancel those out and write that more simple version of the function, we can go ahead and get our whole by following the exact same steps. So it looks like the x-coordinate's going to be negative 3. We plug that into the simplified version of our function, which is x minus 1. That's going to give us a y-coordinate of negative 4, and so that's going to give us a whole with coordinates negative 3, negative 4, okay? So again, later whenever we find wholes of rational functions and draw the complete picture, whenever we move on to drawing the picture, we are going to have to go ahead and draw just an open circle right there on that point to signify that's where the whole is. So not only are wholes characteristics of rational functions graphs, but also these asymptotes are also characteristics. And so what we're going to do in this video specifically is we're just going to focus on these first two types of asymptotes, namely your vertical and your horizontal asymptotes. We're going to talk about this third type of asymptote, a diagonal or a slant or oblique asymptote. We're going to talk about that in a future video, okay? Just so that we're aware, any given example could have this many different asymptotes of these different kinds. So you might find that your example could have any number of vertical asymptotes, but when it comes to horizontal or slanted or oblique or diagonal asymptotes, you're only either going to have one or you're not going to have any, okay? And so that is just kind of something that I'm doing here to give you an idea of what to expect. To find vertical asymptotes, it could not be simpler. It just says in these steps here that we just want to simply take the denominator and set it equal to 0 and then solve for x. Couldn't be easier, okay? So to demonstrate that here in example 6, it just says find the vertical asymptotes here in this picture. I would just simply want to go ahead and take the denominator, which here just looks like a linear 2x plus 5. We're going to set that equal to 0, and we're going to solve. And this makes sense why we might want to do this, because if we figure out what this would be, then this would be the value that if I plug it back in, it's going to equal 0, and that's going to be a problem because this is our denominator. We don't want our denominator to ever equal 0. And so this is going to be where we place that vertical asymptote, because that's going to be a place where the end behavior never touches or crosses, okay? So if you solve this linear here, you're going to get this value, this negative 5 over 2, which is going to be a fraction, but that's okay, right? So this would, of course, be our vertical asymptote in this example. And keep in mind that that is going to be a vertical line. That is going to be a vux. And so that would be something that we would want to draw later on whenever we draw a complete picture of a rational function. Here's another example. This one was one where it looks like the denominator is a quadratic that was already factored for us, so that's pretty nice. If we wanted to set that equal to 0 and solve, that just means we have to set both of the factors equal to 0. And so this would be an example with 2 vertical asymptotes. Remember that any given example could have any number of vertical asymptotes. So this would be an example with 2. The previous example would be one where there's just 1 vertical asymptote. You could have other examples where there are 3 of them, 4 of them. It depends on really what the degree of the denominator is. That's going to tell you how many vertical asymptotes to expect. To find horizontal asymptotes is a little bit more of a pain because we have to split this up into cases, okay? And those cases depend on what the degree of the numerator is. We're going to call that capital N, and what the degree of the denominator is, okay? So again, we've been talking about the degree of the numerator and denominator here for a bit, and basically what we need to be able to do is pick them out so that we can compare them, okay? So it turns out that we split this up into these 3 cases. What if the top degree is smaller than the bottom degree? What if the top degree is larger than the bottom? And what if they are just the exact same degree in the top and the bottom, okay? This down here is the easiest case, the case where you have the degree on the top is more than the degree on bottom, because in that case you don't have any horizontal asymptote to speak of at all, okay? And so I call this being top heavy because the degree in the top is more than the degree on bottom. And so maybe just kind of make the note here, we call this situation top heavy. So if I use that language in the rest of the video, I say I have a rational function that is top heavy, then we can guarantee there that we don't have to worry about horizontal asymptotes at all. On the reverse side of the coin, what if the degree in the numerator is less than the degree in the denominator? I call that being bottom heavy. And if that's the case, then what we see here is that we have an automatic horizontal asymptote, and that is going to be at that horizontal line y is equal to 0. AKA, this is simply just the x-axis, okay? And so that's pretty easy to remember as well. If you're bottom heavy, then the x-axis is just your horizontal asymptote, okay? Really easy to remember. The case that's not so easy to remember is going to be that middle case where the numerator and denominator have the same degree. And if that's the case, then what we do is we just go ahead and make a fraction out of the leading coefficients, okay? And so to demonstrate that to you, I have this little diagram that I stole from the internet here. And what this is it basically just compares the degree of the top to the degree on the bottom in these 3 different cases here. And it gives you some examples, right? So this would be an example that is bottom heavy in this first example. So the degree on the top, it looks like is a linear, so the degree there is just simply 1. And the degree on the bottom, since that's a quadratic, the degree of that would be 2. Okay, so comparing those degrees here, it looks like this is going to be an example that is bottom heavy, and you can take a look at the graph there, right? So it looks like the end behavior is certainly going to be something that approaches the x-axis on both ends, and so we would say here that the asymptote would be y is equal to 0 in this case, aka just simply the x-axis. Okay, in that next example here, it looks like the degree of the top is a 1. The degree on the bottom is also a 1. And so this would be that special case that we'd have to remember. Basically, the horizontal asymptote is going to be the fraction of the leading coefficients here. And so the leading coefficients, remember, that's just the number in front of your leading x term. And so here that is just going to be a 3 on top and a 4 on bottom. And so we would just simply want to go ahead and take the ratio of those 2 numbers. And that is going to be our horizontal asymptote for this case. Okay, and so that's where they've placed this guy is at 3/4 on the y-axis. Okay, next one down, this would be a case that is top heavy. And so you're going to find here, matter of fact, these next 2 cases are both top heavy, right? So the degree on top is 2, the degree on bottom is 1. The degree on top is 3, the degree on bottom is 1. So this would be the case where the degree on top is going to be more than the degree on bottom. So these are both top-heavy. And you can see here that we don't have any horizontal asymptotes in either of these pictures, okay? We're going to find in the next video what it's going to take for us to have an oblique asymptote like there is in that first picture, where we might have a diagonal asymptote to worry about here, but we'll talk about that in the next video, okay? So now what I'd like to do is go ahead and put all this information together, how to find your holes, your asymptotes, and whatnot, and I'd like to go ahead and take you through some examples where we're drawing the complete picture of the graph, okay? So the order that we're going to go ahead and do this in, if you read through these steps here, is we're first going to start off by finding our horizontal asymptotes. That's what we just talked about. So going through all the cases there, figuring out if we're top-heavy, bottom-heavy, or if they're the same. We're going to find those first, and then we're going to draw those. After that, we're going to find any holes that we might have in the graph. Again, we do that using that process of factoring the numerator and denominator, looking for any common factors and canceling them out. And then after that, we take a look at any sort of vertical asymptotes, setting the denominator equal to 0 and solving, and then using all of these different things that we mark on the grid as clues, and then just maybe pulling up the TI-84 to get some nice points to plot, and then that will be a complete problem, okay? And so we are going to go ahead and do this in this order, that would just be the order that I would want you guys to do it to minimize mistakes. So we'll do this first example from scratch just so you can kind of see how this is done, and then we'll flash the other examples up here on screen and call it a video, okay? And so here we have this first function. It is a rational function. It looks like the degree of the numerator is going to be the exact same as the degree of the denominator. It looks like that is both a 2. And so remembering for horizontal asymptotes, what that meant is that the horizontal asymptote is just going to be the ratio of the leading coefficients here. And so the number in front of x on top is just simply a 1. The number in front of x on bottom is simply just a 1. So 1 over 1, that just simply turns out to be 1. And so down here on our horizontal asymptote, I would just simply say y is equal to 1. And that'll actually be the first thing that I draw here on my picture. I could use a straight edge for this, but I'm just going to go ahead and freehand it here. I'm just going to go to where positive 1 lives on the y-axis and put myself a horizontal line there, okay? And again, that's because the degrees are the same. That would just be the ratio of the leading coefficients, all right? Next, we're going to go ahead and move on to finding any sort of holes that we might have in this rational function. And so we're going to do that by factoring the numerator and factoring the denominator. And so since they're both trinomials here, I know that I can just go ahead and use that whole method of unfoiling this that we first talked about in section P.4. So again, make sure to watch those videos if you haven't caught them yet. But here I think a nice combination of 1 and 2 for the top. How about a positive 2 and a negative 1? And then on bottom, I think another combination of 1 and 2 would work nicely. How about a negative 1 and a negative 2? All right. So factoring those, we could definitely see here that we have some common factor in the numerator and denominator. So namely, the x minus 1 is the same on the top and on the bottom. And so continuing to find the whole, we said from before, we would just take that factor that they have in common, and we would just simply set it equal to 0 and solve this. And so if you solve that one stepper there, that's going to give you x is equal to negative 1. And we're going to take that value and we're going to plug it back into the simplified version of our rational function here, which would just look like x plus 2 over x minus 2. And if we plug it back into there, plug in negative 1 in both of those places, we would simply get the following, right? So negative 1 plus 2, negative 1 minus 2, that is going to give us here 1 over negative 3 here. And this doesn't look quite familiar. Let me just check my work here really quickly. I believe I've done everything right so far. Yeah. Oh, wait, hold on. No, I haven't. I did not get, I thought this looked weird. I apologize. So when I solved this this mini equation here, I call that negative 1. That's actually not the case. That's actually supposed to be positive 1. So let me make that error correction. Sorry about that, guys. Done a lot of math today, so mistakes are bound to happen here. So this looks a lot more familiar because 1 plus 2 makes 3 in the top. On the bottom, 1 minus 2 makes negative 1. And so this will give us negative 3, okay? And so I know that I'm going to have a hole at a point with coordinates positive 1 and negative 3. And I'm going to go ahead and write that down here, right? So positive 1, negative 3. As far as the picture, I would just go ahead and go to that location. So go to the right one and go down 3. And I'm just going to go ahead and simply put an open circle at that location, okay? That is going to be the hole in the graph, and then we'll go ahead and draw the path on top of that, all right? And then as far as vertical asymptotes are concerned, remember that we would just want to go ahead and take the denominator and set it equal to 0. We're going to go to the simplified version of my my result here and find the the zeros of the denominator of it. So let's go ahead and simply say here, if OneNote will cooperate, we'll say here x minus 2 is equal to 0, and then solve that one correctly, and that's going to give us x is equal to 2. And so we know that we are going to be able to draw a vertical asymptote by starting at the origin and going to the right 2 units, and that is where my vertical asymptote is going to be. Okay, so by putting all these marks on the grid, we get that much more of a complete sense of what the picture of this graph is going to look like. Okay, and so now to get the rest of the graph, what I might do now is go to the TI and pull up that list of values and get some that might be pretty nice here. Okay, so you notice that I've already gone ahead and done that here ahead of time. I went ahead and typed our example into Y1 here, and if you press graph, this is what the complete picture of the graph would look like. And remember that I'm interested in that table of values, so I'm going to press second graph, and that's going to pull up this table right here. You notice down here on inputs of +1 and +2 that the outputs both say error. And what that means is that, remember, for an input of +1, that's where I had my hole. And so that's why it's going to say error, because I have that hole there in the graph. For an input of +2, that is where we said our vertical asymptote is going to be. So it's also going to say error there in the calculator. Okay, as far as other points to plot here, again, I would just encourage you to maybe pick some input-output pairs that maybe have some nice integers for you to plot. And so if I'm looking around here, I definitely think it's a good idea to pick at least 2 points on each side of the vertical asymptotes, just so you can get a more complete picture of what the shape would look like here. And so if I fill out my table, I'm just going to use some of these integer values here. So that's going to be -2, 0, and then 0, -1. And then some other integer values here. As I keep going, I see 3, 5, and then 4, 3, and I even see 6, 2 there. Okay, so 3, 5, 4, 3, 6, 2. Okay, and you don't have to stick with just those points. Keep in mind, you can use your up and down arrow, and you can go ahead and get some other values to plot if you really wanted to. The more points you plot, the more complete picture you're going to have here. But at this time, I'm just going to go over to the graph and draw some of these points here, right? So we have -2, 0. We have 0, -1, and then we have 3, 5, and then 4, 3, and then 6, 2. Keep in mind, when I'm plotting my points, I am not using my asymptotes as my origin, okay? I'm still going back to the very original set of axes here and using that to find my origin, all right? So you're never going to go from your asymptotes here. We always go from the origin to plot points. And you can see here how the rest of this is going to shake out. I have a nice skeleton of points here, so I can just go ahead and sketch the rest by just drawing that curve. Again, the end behavior, that is going to have to be drawn so that we get closer and closer and closer to those vertical asymptotes, but never touch them or cross them. And you can see here that when I drew that curve on the bottom there, I drew that so that we jumped over that hole that we have in the graph. Okay, and so this would be a complete problem right here, right? So maybe just going through and filling out some of the rest of this information. We can go ahead and fill in my vertical asymptote. We said that that was going to be x is equal to 2. And then from that, we can go ahead and pick out what our domain and range are going to be. Okay, so that would be the set from -infinity all the way up to our problem value. That would be 2 in the case of the domain. Unite that with the set from 2 to +infinity. And then for the range, same thing. We're now just looking at our horizontal asymptote, which is going to cut off at +1. And so we'll write 2 parts united there, and that would be a complete problem. Okay, so using some of those shortcuts that we talked about for how to find your horizontal asymptotes, your hole, and your vertical asymptotes, these would all be things that I would expect you to be able to find yourself and be able to put those on a hand-sketched picture of the graph. Here's part B. Maybe go ahead and pause the screen and check that one out. We do have a hole in that one as well. So you can go ahead and pause the screen on that one to check the work for that. Here is going to be some examples where you have 2 different vertical asymptotes. And so sometimes the pictures of the graphs of these rational functions are going to look a little bit interesting like this, where you might have 3 distinct parts of your graph here. But the idea would always be the same. You want to follow the same exact steps. Find your horizontal asymptotes first. This one would be bottom heavy, so remember that if it's ever bottom heavy, that automatically means you're going to have a horizontal asymptote of the x-axis, which you can see I put a dotted line there for. And then your 2 vertical asymptotes, we get 2 of them here because we have a quadratic in the bottom, and when we set that equal to 0 and solve, we were going to get 2 different vertical asymptotes there. So that would be at -2 and +2. I basically just put those as vertical lines on my grid, and then you can see there that I wrote a note. I just went to the TI-84 to get the input-output pairs that I would want to go ahead and plot here on my picture, and then just go ahead and press graph on the TI-84 to get a more complete sense of what the shape of that graph might look like. okay? And then all the different characteristics down there on bottom. Keep in mind that whenever you point out what the domain is, you're going to have to go talk about that in 3 parts, right? Because there's the part to the left of the first vertical asymptote, there's the part in between the two, and then there's the part to the right of that second vertical asymptote there. And so you can see here that that corresponds to 3 parts on my domain written out, which looks like this down here, right? So I have 1, 2, 3 parts that I would want to go ahead and unite in that way. All right. The next graph over here is going to look even more interesting, and you might be saying to yourself, well, Mr. T, what the heck, man? I thought you said that I couldn't pass through my asymptotes. Well, again, keep in mind, the asymptotes are boundary lines that the end behavior of my curves are going to constantly approach. Sometimes you're going to find that you have a case like this where your curve is going to cross in the middle of one of the asymptotes, but again, if you check the ends, right, so the end behavior is going to be drawn in such a way where it does approach the asymptotes without ever touching or crossing it. So that's more of the idea of the asymptotes than the middle crossing, right? So again, maybe pause the screen and take a look at the work for that one. That would be another example of one that is bottom heavy, so we would have an automatic horizontal asymptote of the x-axis. This would be one that does not have any holes, because when you factor the numerator and denominator, they don't have any common factors, so nothing cancels, so no holes there. And we do have 2 vertical asymptotes because that's a quadratic in the bottom. We factor that and solve, we get 2 vertical asymptotes, and then from that information we can get the domain and range. Okay, so again, a more complete version of today's notes will be in the content library on OneNote, but I hope that this video has been helpful to you. Again, whenever you want to go ahead and draw a hand-drawn graph, here are the steps that you want to take right here. Okay, so I hope this has been helpful to you. If you guys have any questions, then as always, let me know, but that's all I got for this one. Thank you very much for your attention, and I'll speak to you in the next one.